Okay, so having done a brief overview of the basic tools of calculus, the basic idea, remember, is that you should be comfortable with two symbols, one being a D and other being this elongated S. If you see these symbols, you should not panic and run for the hills. You should at least have some idea what these stand for now. Okay, a D is a small change in something, so D by itself is nothing. D also always comes along with something else. That's a small change in that quantity. So for example, the velocity is the rate of change of your position. The acceleration is the rate of change of your velocity. If you can add, you can invert these relations by doing these sums. Okay, so that's the basic idea. Okay, and so today it's okay if you're not able to understand 100% of these things, because the rest of the course is all about applying these tools. Okay, so you see plenty of applications of these things as we move along, starting today. Okay, so today we actually start to analyze one particular physical situation. Okay, which is essentially, remember, we are trying to describe how objects move, how motion takes place. Later on we'll look at why motion takes place. So as far as how motion takes place, let's look at one very simple example. Is, for example, you drop an object. If you drop an object, you want to describe the motion of this object that you have dropped. What's the very first thing that you do? So of course you have some object that you have released, it falls down. So you have that. Of course I've caught it to preserve my joke. But in general, it will keep on falling down until it hits the ground. Okay, so you have dropped some object. How do you analyze the motion of this object? How do you describe the motion of this object? The very first thing that you do is that you first say that, okay, this looks like motion in one dimension. What does that mean? That just means that to describe the position of this object at any instant of time, you just need one number. That's what we mean by motion in one dimension. If you needed two numbers to describe the motion of this object, that would be motion in two dimensions. If you needed three, that would be motion in three dimensions. Why do you need only one number? Well, think about how would you do this experimentally? How will you describe the motion experimentally? How will you, that just means how will you tell me the position of this object at any instant of time? You would place a meter rule, for example, adjacent to the motion of this object, and at different times you would note down the position of this object. You just need 1 meter rule. Okay, of course you'll say, well, 1 meter rule is only 1 meter long, maybe I need multiple meter rules. That's not what I mean. Okay, your meter rule, you can make it as long as you like. Okay, but you just need 1 meter rule. Okay, so in other words, mathematically speaking, you have to set up your axis. You have to set up the orientation of your meter rule. That's one thing. You have to set up where your meter rule starts from. Where's the zero of your meter rule? As in, where is your origin of your coordinate system? Okay, from which point do you start measuring the position? Do you start measuring the position from here, from the point from where you drop the object? Do you measure it from the ground level? If this is your ground level, do you start measuring from there? Okay. Do you orient your meter rule such that this is 0, 0.1, 0.2, 0.3 and so on? Or do you orient such that this is 0, this is 0.1, 0.2, 0.3, 0.4 and so on meters? Okay. How do you, that's what I mean by how do you, where do you place your meter stick? How do you orient your meter stick? Is your meter stick going like that, or is it upside down? Okay. Or in other words, where's the origin of your coordinate system? What's the orientation of your axis? Okay, these are your two choices that you'll be making throughout this course. Whenever you want to describe your motion, the very first thing that you need to do is to set up a coordinate system. That means that you decide where is the origin of my coordinate system. You also decide what's the orientation of my axis. Is one choice better than others? Not directly. Every choice is equally valid. It's just that some choices can be more convenient than others. Okay, so every choice is as physically valid as any other choice. Okay. So for example, I set up my axis such that I start measuring positions from here. So this corresponds to x is equal to 0. And I do it in such a way that my meter rule is pointing downwards. So for example, this is 5 centimeter, 10 centimeter, 15 centimeter, 20 centimeter, and so on and so forth. Okay, so x is increasing downwards. That means that if I want to describe positions above this, then of course I have to use negative numbers. That would be minus 10 centimeters, minus 20 centimeters, minus 30 centimeters, and so on. Is your good old number line that you did, way back once upon a time. Okay. So it's the same thing. Okay, so that's what I mean by the orientation of my axis, and then the object falls down with the orientation I have chosen. That okay, here's the origin of my coordinate system. This is my axis. That's the direction of my axis. That's the direction in which x is increasing. Okay, according to my meter stick. If I then ask you plot a graph that shows the behavior of x versus t. What is x? X now is the distance fallen by the object. Okay, if I ask you plot a graph of this function, what will you plot? You essentially will be getting what? So you first of all say, okay, this is motion with constant acceleration. We already solved that, okay, what's the function that describes the position of an object moving along one straight line with constant acceleration. That function, if you recall, was x naught plus ut plus half at square. Right? Where did this come? You don't need to memorize this, although if you haven't memorized this by the end of the course, maybe you didn't open the book enough number of times, okay? But anyway, this is just a result that you obtain by saying that the acceleration is constant. That means that if you integrate a is equal to dv by dt, you get v is equal to u plus at. The velocity being a linear function, you integrate that to get the position, you integrate u plus at, that's what you'll get. Okay, that's how you essentially make sure you understand how to get this. Okay, are the derivations coming in the exams? Maybe yes, maybe not, but indirectly they always are. If you don't understand the derivations, you don't really understand much of anything. Okay. Okay, anyway, so you have this. U and A could be positive, could be negative, depends on the situation at hand, depends on how you set up your axis. Okay, so this equation, the way I've written it, that does not mean necessarily that U has to be positive and A has to be positive. Okay, it depends on the situation. Okay, so for this situation, what is x naught? X naught is 0 because x naught is the position of the object that I've dropped at the instant when I started my clock. So I started my clock implicitly just after I dropped the object. Just after I drop the object is at the origin. That's why it's a convenient choice to set your origin over here, because then immediately this thing becomes 0. If I had set the origin at the ground level, then x naught would just be, if this height is h, I'm dropping this object from height h, then this x naught would be h. Okay, because that's the position of the object when I started my clock. I always start my clock just after I drop my object. Okay. Of course, I was to say that I started it 10 seconds before I dropped the object. You could do that, sure, but the motion in the 10 seconds in the 10 seconds before you drop the object is very boring. The object is just there stuck at x is equal to 0 with this choice of coordinate system. You don't really need to consider that. Okay. Okay, anyway, so what's the graph then of x versus t? Where do I draw? This is the origin. As time goes on, this is 0. You are getting this ut plus half at square. Okay, so if I dropped it from rest, which just means that I just released the object, I didn't throw it downwards, that means that u is 0. Okay, so if I just release it, I could have thrown it, of course. That's a slightly different situation, which we can look at very soon. Okay, but let's start from the simplest possible situation. You just release the object. In that case, you just get that x is equal to half at square. And since this is acceleration in the free fall, this is equal to half gt square. Many people have this weird kind of fascination that, okay, since it's falling downwards, the acceleration must be negative. It could be positive, it could be negative. It depends entirely on how you set up your axis. The way I have set up my axis, the axis is pointing downwards. That means that as time goes on, x is becoming more and more positive. That means that I need to have, it's for sure short, for this case, I need to have a quadratic function. I need to have, the graph must look like a parabola. There is no other way around it. The only possible confusion over here is, of course, is it a parabola that goes like that, or is it a parabola that goes like that? And of course, given the way that you have set out your axis, x keeps on increasing. That means that the parabola that you are talking about must be like this. That's basically your graph of x versus t. Okay? It cannot be a straight line physically, because as the object falls, it speeds up. If it was a straight line, then that immediately implies that the speed of the object at any instant of time is the same. But if you have ever learned anything from your throwing objects in your life, you know that that is not true. A falling object speeds up as it falls down. Okay, remember the slope of this graph at any point tells you about the derivative of this function, which in this case physically means the speed of the object. Okay. Right? Okay, so if I now ask you what's the graph of the velocity versus time of this falling object, what do you plot? You just draw a straight line through the origin. By the way, notice over here I made this graph pretty much flat near the origin. Why did I do that? Because I know that the slope of this graph at the instant when I dropped it needs to be 0. The slope of the tangent line at t is equal to 0 needs to be 0, because that slope represents the initial velocity of this falling object. I just release this object so that initial velocity is 0. So that's the graph that you have. Okay. You know it should be a straight line because you are looking at the derivative of a quadratic function. Once you take the derivative of a quadratic function, you get a linear function, and that's exactly what you have over here. Okay. Right? And of course, going back, how did you get the velocity in the first place? You integrated the acceleration. You integrate the acceleration, you get a linear function for constant acceleration. That's exactly what you have over here. Right? If I then ask you plot the acceleration versus time, what do you get? You just get a straight line with a positive vertical axis intercept. Okay? So and this numerically, this is equal to g, approximately 9.81. In this course, I'll just take 10 meters per second square. Okay, that should be the least of your worries. Should I take g 9.81 or 9.8 or 10 meters per second square? Doesn't matter. For all I care, you can do it on the moon. Okay, as long as you state that I am doing all these experiments on the moon, I don't care. Okay, but unless stated otherwise, try to remain on Earth. Okay, I know you like to throw something with your hand and that thing immediately escapes to space, but try not to let that happen. Okay. Anyway, so that's what you have. By the way, g itself is just a positive number, 10 meters per second square. If it's a negative acceleration, I'll be writing minus g. Okay, as in this symbol itself does not contain any sign. It's just a positive number. Okay, right. So don't get confused by that. Okay. Anyway, so you now know how the position is changing with time. You now know how the velocity is changing with time. You now know what's the acceleration experienced by the object. It's very easy to make mistakes in problems such as these regarding the signs. It's very difficult to make a mistake if you draw some rough sketches of what's going on and then still be able to make a mistake regarding the signs. Okay, it requires a special talent to do that. Some of you do have the talent, some of you thankfully don't. So try not to have that talent, okay? Just quickly sketch curves regarding what is going on. And then make sure that whatever mathematical function you are writing, those functions should be consistent with the curves that you have plotted. Okay, just be careful about that. Now suppose instead of this your friend comes along and says, no, I will choose the standard axis in which distances increase upwards. It's exactly the same situation. Nothing whatsoever changes with regards to the falling object. It's the same falling object which is falling. We are just using a different coordinate system to describe the falling object. The mathematical functions will change. X of t will now look slightly different. V of t may look slightly different. A of t may look slightly different. But the basic physical results will be exactly the same. If I asked you, what's the time taken for this object to hit the ground? That time will be the same no matter which coordinate system you use. Okay. So anyway, so if you use this coordinate system, I say, okay, let's choose a different just to convince you. I use a different coordinate system. This coordinate system. My axis is pointing upwards. And I use this as my origin. So now x is equal to 0 is over here. X is equal to 0 is at the ground level. What is x of t now? You tell me. What is x of t now? Again, I just released the object. I haven't thrown the object. X is equal to, what's x naught in this case then? H. H is the height from which I've released the object. Okay. And what is u? Again, assuming that you release it from rest, u is 0. And what else do you get then? Well, you get plus half gt square or minus half gt square. I don't know. Okay. Again, it's very easy to get confused over the sign over here. But before writing this down, like I said, just draw a sketch of x versus t. At t is equal to 0 now, your object is over here. Is at height h. That's where the object starts off from. Given your axis, as time goes on, does x increase or does it decrease? Let me just remove this so that you understand it. As time goes on, does x increase or decrease? Remember, this is 0, and now the way I've set up my axis, this is 0.1, 0.2, 0.3, 0.4, and so on and so forth. As time goes on, x decreases, and it has to decrease parabolically. Essentially, it's still going to be a parabolic, it's still going to be a quadratic function. So the only way to do that, of course, is this. Once again, the slope of this graph at t is equal to 0 needs to be 0, because that again is the initial velocity of this object. But again, now look, this function looks very different from the function you had before. Now sure, it's quadratic, but it's not exactly the same by any means, although it is exactly the same object. Okay? And now it's very easy to figure out the sign. Given the shape of this curve, the only possibility that you can have is that this must be h minus half gt square. Okay? It's very easy to get the sign correct, using equations once you have done vectors. But right now, it's very easy to get confused regarding the signs. Okay? So you release this object. You release this object essentially from height h. As time goes on, the x coordinate decreases. I cannot, if it was h plus half gt square, which many people are fond of doing, that's the curve. And that means that if I ask now the question, what happens to this object at long times, it has escaped to infinity, which is of course utterly nonsense. That goes against the very English language meaning of the thing falling down. This is not even falling down, this is falling up. Okay, whatever that means, okay. Okay. G के साइन का, okay, so ये ग्राफ ठीक है, and this is an inverted parabola. If this was h plus half gt square, आपका ये parabola ऊपर की तरफ जाता. Another way to see that is, okay, given this graph, given this wide curve, plot the function t versus v. What do you get now? Well, just look at this function. Initially इसकी slope 0 है, and then the slope becomes more and more and more negative. It becomes bigger and bigger in magnitude, but becomes more and more negative. And it has to be a linear function because this is a parabola. The derivative of a parabola is a straight line. So you get that. Okay? Right? And then if you differentiate this, you get the acceleration time graph. Why do you get that? This is a straight line with negative slope. Constant negative slope because it is a straight line. That's what you get. And hence the acceleration has to be negative. How negative? Minus g. Okay? Always make sure that you, at least at freshman level, at first year level, it's very easy to think about the problem in with different approaches. Make sure that your different approaches agree with each other. That's one very good way to check your answer. Maybe not fully, but at least simple graphical sketches should agree with the mathematical functions that you are writing down. Okay? Okay, so much for that. Let's make the problem more difficult. Suppose I've dropped this object, and then my friend who's standing at the base of a tower, so let me just explain the situation now. So you have a tower, you have your essentially your friend who's standing at the base of this tower, and you have this object. So let me call this object A, and I'll call the second one object B. So now there are two objects. And you have to simultaneously analyze the motion of two objects rather than a single object. So I release this object B, of course, from rest. I just release it, it falls down. Okay? My friend, at the instant when I release this object B, my friend throws this object A upwards with some speed u. The question is, at what time are the two objects at the same vertical level? Okay? Right? That's basically what you have to look at. Of course, here you might be saying, well, once this object falls down, maybe it's an elastic ball, maybe it starts bouncing up and down. This ball goes up, slows down, comes back, and then it also starts bouncing. So aren't there multiple instances of time when they are at the same vertical level? Well, essentially, I stop my clock as soon as one of the objects hits the ground. So I'm basically interested only in the first instance when they are at the same vertical level. I'm not really interested in what happens after that. Okay? Ball B is just being released from rest, so it just falls vertically. Okay? Of course, I've thrown them slightly side by side so that they don't collide with each other. Okay, but that horizontal separation is not really important over here. Okay, so how do I do this? Again, you have to set up a coordinate system. And again, the choice is yours. Once you choose your coordinate system, aka you set up your origin, you set up the orientation of your axis, stick to that choice. Don't change your mind midway through. Do not describe the position coordinate of one ball in one coordinate system, the position coordinate of the other ball in some other coordinate system. Use the same coordinate system. Okay? Then, so we have to set up our coordinate system. Let's do that. Which one do you prefer? Okay, so let me do this one. X is equal to 0, the axis is pointing upwards. That means again, x is equal to 0, 0.1, 0.2, 0.3, 0.4, and so on. So if I want to describe the motion of object A, what do I do then? Let's plot a graph of x versus t for object A. What do I get? What do I draw? ये भी curve है. Okay. What kind of curve? Where do I start it from? 0. Because object A is initially at the origin. So that's where it starts off from. Okay. And then what happens? Is it like that? Is it like this? What is it like? So remember, you are throwing the object A upwards. So you start your clock just after object A has been thrown, and simultaneously that corresponds to just after B has been released. Okay. So just after A has been thrown, object A does have some velocity. Just after. Okay. So many people confuse this. Okay, well, while it was in your hand, what is object A doing? Not important. I hadn't started my clock yet. I'm not really interested in what happens to this object A while it was in my hand. I'm really only interested in the motion of object A once it has let go of my hand. To analyze what object A is doing while it is in my hand, of course I need to know the forces acting on object A while it is in my hand. But I don't know those forces unless you tell me those forces. But I don't need to know those forces anyway to analyze what time are these two objects at the same vertical level. Okay. So this graph goes like that initially, because you need a you need a tangent line that looks like that, a tangent line with positive slope, and that is obvious from this coordinate system. As time goes on, the x coordinate for object A increases, but it then starts to increase at a slower and slower rate because the object is slowing down. So therefore you have to make it flatten. And then eventually a time comes when this object A is instantaneously at rest. That is of course over here when this curve is completely flat. And then object A starts falling down. Okay. That does not mean, by the way, that while this object A is going up, acceleration is minus g, while the object is coming down, the acceleration is plus g. That is utterly nonsense. The acceleration is minus g in this case throughout. Okay, right? As you will see once we plot the velocity time graph and the acceleration time graph. A much easier way to see that, because you have done Newton's laws, you know some idea about forces from high school, is that, okay, where is this acceleration for that object A is experiencing, where is that coming from? Which force is responsible for the acceleration that object A is experiencing? Gravity. And gravity is always pointing downwards. Whether object A is going up or whether it's coming down, gravity always points downwards. So then how can the acceleration change midway through the motion? Okay, it doesn't. Okay, you are confusing the word acceleration, the physical meaning of the word acceleration, with the English language meaning of the word acceleration. Okay, anyway, so then of course this goes like that. And eventually it hits the ground again. That's it. At this instant of time, the object is instantaneously at rest. Again, you should be able to translate this mathematical picture to a physical picture. You should be able to, if given a graph, you should be able to describe the motion of the object in simple words. How is the object moving, given I showed you a picture of a graph? How is the object moving, given I showed you some mathematical function? Okay. Now, let's come to object B. This is again, remember, height h. So if I come to object B, what does that look like? Well, okay, it starts from height h, and then you have something like that. That's what this function looks like. Okay. And if you want to find out the time at which they are the same vertical position, what do you do then? You need to look at essentially the coordinates of this intersection point. Because at this point is the x value for both these objects the same, which means that they are the same vertical level. Okay. And how do I find out the intersection point? Well, now it's straightforward. This has equation h minus half gt square. I don't need to rederive it, we just did it. This blue curve is described mathematically by the equation x naught for this object A is 0, u is positive. Look at this. At t is equal to 0, is the slope of the curve positive or negative? Positive. So u is positive, so you get ut, and this is an inverted parabola. So you need minus half gt square. That's the mathematical equation for essentially the object A, and that's the mathematical equation for object B. Okay, and you can set them equal to each other and just solve for t to find out the time at which the two objects are at the same vertical level. Easy peasy, because actually minus half gt square cancels out. Okay, so much for that. Now I ask you, is it always true that there will be that the both objects will be at the same vertical level? Would it always be true that the two objects will be at the same vertical level? Okay, if you say no, give me a counter example. Give me a physical situation in which both objects won't be at the same vertical level. What do I need to do such that they are never at the same vertical level? Okay, what do I want? Exactly. So if you throw object A like this, like yellow, ye main phenka, or my friend from a very high tower releases an object, I was able to, this object basically hit the ground before the second object ever got near to this first object. In other words, this blue, who's to say that this blue curve looks like that? Maybe it's a much shallower parabola. And then of course the equation is still ut minus half gt square. The only difference is that u is much smaller for this parabola. What's this point? What's this? This is the maximum height to which this object A rises. That of course depends on u. You can immediately see that it depends on u because you have ut minus half gt square. At what time, what does this time correspond to? What is this time? How do you find out this time? You just find out, or you say, well, okay, at this point the velocity of this object is 0, aka the derivative of this function needs to be 0. What's the derivative of this function? U minus gt, that has to be set equal to 0, and therefore t is equal to u over g. That's this value of time at which this object that I've thrown up is instantaneously addressed. You throw it with a smaller velocity, of course, this point at which the object is instantaneously addressed comes about much quicker. Okay? Blue? तो पहले बता देते. Okay. लैला मजनू की कहानी सुन के लैला मर्द थी या औरत था? Okay. येलो ठीक है? पिंक ठीक है? ओके. अच्छा चलो मैं क्वालिटी कंट्रोल पे करता हूँ. ये ठीक है? ओके. चलो ये भी ठीक है. तो नो मोर ब्लू हो गया. Anyway. Okay, so let me just sketch it very quickly. Yeah, this is object A. This at least you can see, hopefully. This is object A. If I've thrown the object A with a very small velocity up, what's the value of time for this? As in, at what value of time is object A instantaneously addressed? For what value of time is object A at the highest point in its trajectory? Okay, that time we found to be u over g. And what's the corresponding height? What's this? How do I find that out? Well, you just put this value of time back in this function. So you basically get u times u over g minus half g, and you get t square. So you get u square over g square. and you are basically getting u square over g minus half u square over g, because this g cancels one of these g's, and this is whole thing is just half of u square over g. The smaller speed with which you throw it up, the less distance the object rises, of course. जितनी जोर से ऊपर फेंकोगे, जितनी स्पीड से ऊपर फेंकोगे, उतनी ज्यादा तेजी से ऊपर जाएगा, उतना ज्यादा हाइट तक जाएगा ऑब्जेक्ट. Okay, and it's a quadratic function, so it increases very rapidly. Okay, right. So this is half u square over g. If this half u square over g is smaller than h, they are not going to intersect. Okay, right. Acha. The next thing that you need to, so make sure that you draw these sketches, because I have seen it many times that what happens. These two curves, if you look for their intersection point, many students don't realize that essentially if you draw a sketch, what happens? They just they just say that this is equal to that, and they try to solve it mathematically. Okay, but if you actually plot these sketches, you realize that okay, over the region of interest that you're dealing with, in this region of the graph, there is no intersection point. Okay, so always make sure that your answer makes physical sense. Your function that describes motion is only true for some values of time. If you are writing down half gt square, that is only true until the object is above the ground level. Once it hits the ground, this function does not describe the position of the object anymore. If I release this object and say, well, where is the object 1000 seconds from now, half gt square is not going to do it, of course. Okay, so all these functions that describe motion come along with their specific domains, if you want to put it mathematically. Okay, always make sure that you're dealing with the correct values of time. Okay, let's make it slightly more complicated. Again, exactly the same situation. Yeah. G is positive. G का पूछ रहे हैं? G पॉजिटिव है या नेगेटिव बताओ. पहली तो बात है नेगेटिव होगा इस केस में, मतलब एक्सप्रेशन इज नेगेटिव. G itself I always take to be plus 10. So if expression is negative, in this case I will be writing expression as minus g. दोनों ही नेगेटिव हैं. दोनों केसेस में कौन सी फोर्स लग रही है बॉल्स के ऊपर? नीचे की तरफ. तो एक्सप्रेशन कैसे दोनों की डिफरेंट हो गई? तब भी वही है. So okay, look, for the object that I have thrown up, that's the graph. If I plot now the velocity versus time function, what do I get? Initially you have positive velocity, it becomes smaller and smaller, it reaches 0, then it becomes negative. Negative velocity just means that it's moving downwards. If I say what's the acceleration versus time graph, what's the slope of this thing? Negative. It's a constant negative value, it's a straight line. This is for the object that I've thrown up. Now for the object that is falling down, x versus t is, its velocity is initially 0 hai, or the acceleration is again that. अब वो इंग्लिश लैंग्वेज जो स्पीड अप और स्लो डाउन का बड़ा मसला होता है. यू ऑलवेज हैव टू टेक इनटू अकाउंट के वो डायरेक्शन क्या है. Only bothers to throw this object A upwards 5 seconds later, for example, or time td seconds later. There's a time delay. Then I have to find out, okay, now at what time are the two objects at the same vertical level. Okay, now what do I do? Is that I start my clock just after I released my object. That's what I get. So t is equal to 0 corresponds to the time, to the instant when this object graph of position versus time for this object A. That's what it initially looks like. It remains at x is equal to 0 until some time td, t subscript d, time delay. Then the object is thrown upwards and it moves like that. Of course, the actual graph depends on what u is, as we just saw. Okay. Now, if I want to describe the yellow curve mathematically, yeah, ठीक है. Did everybody get why essentially I have this horizontal section, then I have this parabola? Okay, great. So this is h minus half gt square, exactly the same as before. But how do you describe this curve mathematically now? Yeah, so essentially what do I write? U t minus td minus half g t minus td whole square. That's the mathematical equation that describes this curve. Is the original parabola is shifted td time to the right. You can check this. If td is 0, what should you get? You should get back the original parabola, ये जो आपने ये बनाया था, for example. If td is 0, you get back exactly that. The advantage of doing all these things in terms of variables rather than numbers is that you can play around. Think about, okay, what happens if this quantity equals that? What happens if this quantity equals that? Because your equation should generally be true. If you straight away say that td is 5, then you are essentially doing a very special case, where td can only be 5. But if you leave it as a symbol, then you can explore around, you can play around. Okay, what happens if td is this? What happens if td is that? Okay, so if you had mistakenly put in a plus over here, then it's very easy to check your answer, right? Because if you essentially, if you are getting essentially that td is, for example, 10 seconds, then essentially you're going to get a very big number over here. Okay, for t is equal to 0. For t is equal to 0, you get a big number over here if td say is 5 seconds or 10 seconds. But that is not true, because at t is equal to 0, आपको पता है उसका x 0 ही होना चाहिए. It's only after 5 seconds does it bother to move. Okay, so it cannot be plus. Always make these little checks along the way, okay? It's utterly useless in physics to actually go line by line and check your algebra. That's the way nobody checks their answer that way. You at the end, it's very easy to check your answer in physics. Does my answer make physical sense? Is everything consistent with everything else? That's it. If it is, there's a very high probability you did the algebra right. If things go off into space, of course, with 100% probability there's something wrong. Unless, of course, you are Hercules or something, okay? Okay, so always make sure of that. Okay. So with that done, by the way, remember that ut plus half at square plus x naught is equal to x of t. We derived this by integration. And we said that essentially if there is an object that is moving with constant acceleration, that's what this function will look like. That's what the position of this object will look like as a function of time. But now we are saying that for this object, the object that my friend has thrown upwards, the function looks like this. This is not of that form. Where does this TD appear? ये किधर से आ गए mathematically? I mean, you were able to figure this out by looking at by ये curve shift हो गया. But what went wrong in the derivation of this that now TD appears? इसलिए मैं कहता हूँ सारी गेम ही डेरिवेशंस की होती है. If you don't understand where the things come from, you don't understand how they are linked to each other. If you don't understand that, you start applying everything in the wrong situation, in the wrong scenario. किधर आएगी? How is TD appearing? V is equal to dx by dt होता है. V is equal to u plus at for an object experiencing constant acceleration. You plug this thing over here, you integrate this, and you get that. For the motion of an object moving with constant acceleration. And yet I have produced a concrete example for which the motion of the object is not described by that. It's described as something different. कुछ तो some idea, yes. जिसका क्या मतलब है? वो तो x नॉट पे चला गया है, लेकिन ये देखो ये t के साथ td किधर से आ गए हैं? This is not x नॉट. इधर देखो एक और क्रॉस टर्म भी तो आएगी. Once you expand this, you'll get minus 2t td. वो कांस्टेंट तो नहीं है. सिंपल सा सवाल है. किसको एक्सप्लेन? इसको तो हो जाए माइनस. लेकिन मैं कह रहा हूं ये इस फॉर्म का तो नहीं है ना. यू एक्चुअली गेट, वंस यू एक्सपैंड दिस, यू एक्चुअली गेटिंग अ क्रॉस टर्म minus 2t डी. वैल्यू क्यों होगी यार? वही ये कर्व ये है, ये कर्व ये है. For the same value of t, there are very different values. t को माइनस कर रहे होते हैं. Close. Essentially, this is derived under the assumption that. Thank you, TD0. That is obvious from that function TD. That this is derived under the assumption that you start your clock as soon as the object starts moving, as soon as you get interested in the motion of the object. But here, for this object, the object does not start moving at t is equal to 0. It only starts to bother moving at a time td. In other words, वापस जाओ ड्राइंग बोर्ड पे. dx is equal to v dt. ठीक है. Now add them up. So if you add them up, what do you get? You get x naught x dx prime is equal to the initial time. अब इनिशियल टाइम क्या होगा इस ऑब्जेक्ट के लिए? ये टाइम t, ये आपका आ गया इधर से u प्लस a. अब इधर t प्राइम डालूंगा. ऑफ कोर्स नॉट. ये आपका वेलोसिटी फंक्शन में भी तो t दी जाएगा. इफ आई एक्चुअली बॉदर एंड से कि भाई a इज इक्वल टू dv बाई dt, then I get from here that dv is equal to a dt. And then if I add now both sides, what do I get? I get dv prime u v is equal to a dt prime from which time? td to t. और ये एक्सप्रेशन कांस्टेंट है, so this becomes a times t minus td. इसको मैंने प्लग करना है इधर, so I get this is t prime minus td. और फिर इसको इंटीग्रेट करो. Once you integrate this, I leave it as an exercise, you just get that. Of course, doing it via integration is much more complicated compared to just sketching a curve and immediately being able to figure out, oh, ये तो पूरा curve displace हो रहा है. Okay. If you integrate this, ये u constant है, ये बाहर जाएगा, you put in the limits, you get u times t minus td. You integrate this, you're going to get half of t prime minus td whole square. You put in the limits, you'll get half of t minus td whole square. Or a of course साथ है, so you just get that. Now a of course minus g here. Yes. Because you needed the speed, right? To find out the distance, you need to know how does the speed of the object change as a function of time. फिर आप बता सकते हो distance किधर है वो. Because you know the relationship between position and velocity. जो कि आपका ये है. Knowing this, you can figure out x. But you don't know this yet. तो इसलिए पहले मैंने ये figure out की है from this. And then once I figured this out, I plugged this into over here to figure out x. ये exactly वही है जो पहले किया था. Okay? Now the derivations are important because if you understand the derivations, you understand the assumptions that go into each and every one of those equations. Only by understanding those assumptions can you then not make the mistake that you apply an equation to a situation where it doesn't apply. So if you didn't understand this assumption, you didn't bother to sketch the curves, it's very likely that you would have considered that, okay, the mathematical equation that describes the position versus time for this object, for object A that has been thrown upwards, is just ut minus half gt square. You would have missed this td factor altogether. Okay? Okay, so much for that. So we are done with essentially motion in 1D. Now I need to start talking about motion in 2D. We'll continue next time, of course. Okay, so you want to describe motion, you want to describe motion in 2D. Okay, what do you do to describe motion in 2D? Okay, the first thing that you need to understand is motion in 2D means that you need two numbers to describe the motion of the object. Okay? That means that you have to essentially take a lot of inspiration from what has already gone on. That means that you need to think about where do I set up the origin of my coordinate system, how do I orient my axis. Okay, so that's what you have to do. Okay. So as a concrete example, imagine that you have the surface of this board and there's some insect that is crawling on the surface of this board. And I want to describe the motion of this insect. The insect, of course, can move left and right, it can move up and down. Okay, so how do I describe the motion of this insect? How do I specify the position of this insect at any instant of time? How do I specify the velocity of this object, of this insect at any instant of time? How do I figure out the acceleration of this insect at any instant of time? Those are basically the questions that I have to deal with. Okay. Once you understand how to do it for this simple problem, you can do any three-dimensional problem as well. The mathematics is very, very similar. Okay. Okay, so you have your insect, say over here, and you want to describe the position of this insect. So taking inspiration from what we have already done, the first step is that you set up a coordinate system. But now you don't need just one axis, you need two axes. Because you don't just need to specify how much to the left or right this insect is at any instant of time, but also how above or below it is. So you basically have to first of all say that, okay, I'll measure position from some origin. And then you set up a coordinate axis. You could choose your coordinate axis like this and this. You could choose it like this and this. You could choose, any orientation of your axis. But the x-axis, it's convenient to have that perpendicular to the y-axis. I use the usual So I made the usual choice that the x-axis is horizontal, the y-axis is vertical. Okay. But that's not necessary. Okay, now you want to describe essentially the position of this object. The easiest way to think about how to do that is that, okay, I construct this mathematical object that joins the position, the location of my origin to the location of the insect. That mathematical object I pictorially represent by this arrow. And I call that, I say that this is the position vector of my insect. I write R and on top I put an arrow to show that this is not just a number. This is not a shorthand for a number, it's shorthand for this special quantity, this mathematical object, okay, that tells me essentially both how far the object is from this point, from my origin, but also where the insect is located. What's the direction in which I need to look at in order to see the insect? Do I need to look, like this direction? Do I need to look up with respect to the origin? Do I need to look to the left? Do I need to look below? Okay, so that's why we say that, so this is an example of a vector. A vector is a quantity. ज़्यादा ही बोलने शुरू हो गए हो, पीछे गप्पे मार रहे हैं बैठ के, अच्छा खासा शोर होता है इधर, बात कोई थोड़ी देर पेज पे कंट्रोल कर लिया करो, माना कि जिगरी जा रहा है, खोखे जाके जिगरी बंद खत्म कर लेना अपना, हो गया आई डोंट जज, ओके जो भी करना करो, ओके क्या हुआ? ओ आई अगेन यूज्ड ब्लू, ये लो जी आपका ये है. Okay, so this is your position vector, an example of a position vector. The whole strategy will be to analyze how do I describe this position vector mathematically, how can I manipulate these position vectors. From these position vectors, how can I extract some idea of how fast the object is moving, some idea of how fast the velocity is changing. क्या हो गया यार, बस करो, नहीं बातें करनी है, बाहर चले जाओ. अच्छा, okay, so that's our basic idea. So the first thing we have to do is to learn how to manipulate these quantities called vectors. And you mostly have some idea of how to do that already. We all know that, okay, an arrow is basically an arrow with a tail. That's the tail, that's the head. The arrow part is the head, this is not the tail, this is known as the head of your vector, okay. So if you have two vectors, how do I add them? What does that mean? Okay. The whole rules for manipulating vectors come about simply by thinking about what happens if you walk around. If I take 2 steps to forward and 2 steps to the right, where do I end up? Well, I end up in some diagonal orientation with respect to the original point. If essentially you're asking about what's my position relative to my initial starting position. That's what I mean by adding vectors, essentially. You take your first vector that describes the change in position, aka displacement. A displacement is a change in position vector. Okay, so you take your first displacement, you take your second displacement, and now I know how to add these two vectors. That's your total displacement, and I have some idea what do I mean by total displacement. Okay, right. So, for example, I move from here to here, and then I move from here to here. What's my total displacement? That's that. So if I say that A is my first displacement vector, B is my second vector, displacement vector, but essentially all rules for manipulating vectors follow exactly the same rules as displacement vectors. Displacement vector is essentially your prototype of vectors. All rules that you get for manipulating vectors follow from thinking about what happens with displacement vectors. Okay? And this is C. Essentially putting A and B together, just like you have one block, you have another block, you put them together, you say I have 1 plus 1 equals 2 blocks. I have one arrow, I have another arrow, you put them together, and I have this arrow. So by the same analogy, we write this as that C, this arrow C equals the sum of arrows A and B. This is just shorthand for this process. that you draw the first arrow, you link the tail of the second arrow with the head of the first arrow, and now we understand what we mean by the sum. The sum is the arrow that joins the tail of the first arrow to the head of the second arrow. That's where this head to tail rule comes from, but it's obvious, okay, if you just walk around. Okay. Then you can say that you can think about, okay, other things. What if B is equal to A? That means that I take 2 steps in some direction, for example, and 2 steps more in the same direction. What's my total displacement? 4 steps in the same direction as the first vector. As in, if I then have essentially that if I have a vector A, I move in exactly the same vector using the basic definition of multiplication, that 2 plus 2 can also be written as 2 times 2. 4 plus 4 can also be written as 2 times 4. So, using that as my inspiration, I write this as 2 times A. I am just writing it as 2 times A. But now I have to interpret it. Iska matlab kya hai? But I now know what this means. This just means that this is basically that if I took 1 step in some direction and then 1 more step in the same direction, that is equivalent to taking 2 steps in the same direction as A. As in other words, this is basically a vector of the same direction as A, but double the size. Okay? So let me just keep on summarizing what we are learning about vectors over here so that you don't get lost. Okay, so see, we have learned about how do you add these arrows. We have learned about k times A, where k is bigger than 0. I haven't yet talked about what is minus 2A or what is minus 5A or what does it mean to consider the negative of a vector. To deal with minus 2, for example, how do you define a negative number, by the way? The बड़े mathematician. नहीं, negative में number की बात कर रहा हूँ यार. How do you define minus 5? Minus 5? 5 less than 0. Okay, yeah. So that's a good. That's a start. But to make this definition, you had to introduce something else. Minus 2 is the number such that when you add plus 2 to it, you get 0. That's how you define any negative number. The negative of x is the number such that when you add x to negative of x, you get 0. Okay, anyway, so in exactly the same way, I'll define the negative of a vector in exactly the same way. I first define the 0 vector. 0 को कैसे define करते हैं? Or normally, how do you define the number 0? The number that does nothing when it comes to addition. 0 is a unique number that when you add it to any number, you get the same number. So I define the 0 vector in exactly the same way. The 0 vector is a vector that is your favorite vector. Do nothing. You add it to any vector, you get back the same vector. So in other words, I move 2 steps, for example, and then I just कुछ भी नहीं करना मैंने. That's the 0 vector. So in other words, 0 vector is the vector such that A plus 0 vector, I'm putting an arrow on top that denotes that this is a vector, is equal to A for every arrow A, for every vector A. That's the 0 vector. It's exactly the same as how you construct the 0 number. And then how do you construct, given x, how do you construct minus x? You can now talk about, okay, that minus x is the number that when you add it to plus x, you get 0. In exactly the same way, what do I mean by minus a? Minus a vector should be the vector such that when I add to it to plus a, the original vector, I get the 0 vector. So I say, okay, minus a plus a should be equal to 0. That allows me to figure out what minus a is. So, okay, मैं 2 steps आगे लेता हूँ. I need to think of what vector do I need, what do I need to do next in order to get the 0 vector. क्या करूँ मैं? 2 कदम पीछे ले लो. You get back to exactly the same starting position. In other words, you have an arrow A. What vector do I add to this arrow A such that I get back over here? Now I understand what minus A means. That's why it is a vector pointing in the opposite direction of exactly the same size. Okay, of course, आपने रट्टा मारा था स्कूल में, मैं भी ना. Now कोई logical sense होती है कि किस तरह construct होती हैं चीजें, but anyway. So now you understand what is the meaning of minus A. As in this defines the zero vector. So this defines essentially minus A. So you need to understand how does the meaning of minus A being a flipped vector. How does that come about? Okay, and then you can think about, okay, what is minus K times A, where K is positive. So I've explicitly pulled out a minus sign. This you say, well, this is first, you essentially stretch vector A by a factor K, and then you flip it. So minus 3A is a vector that is 3 times the size of vector A, but flipped, but in the opposite direction. Okay, so that's where all these basic rules of vectors come from. Just by analogy with how you, again, just by extending, in other words, what we did in 1D. 1D के अंदर मैंने एक simple सी real number line essentially इस्तेमाल किया. I use the rules that apply to that simple real number line. I extended those rules to essentially these arrows. These are basically the same rules as your real number line, except that now I'm dealing with arrows rather than just numbers. Okay, that's how it always goes. You use what you already know and try to extend it, try to generalize it to the more complicated situation. Okay, I still have 5 minutes by the way. 5 minutes बाद मैं शुरू करता हूँ क्योंकि आपका अटेंडेंस के तमाशे नहीं खत्म होते. Okay, टहल पहल के आराम से आ रहे होते हैं यूं जैसे ना ऑनररी अटेंडेंस लेने आ रहे हो, सर पे मेहरबानी गा रही हैं शो अप करके. Okay. Okay, so the next thing that you have to do is to essentially we have to formulate a smart scheme to manipulate vectors using these rules. This is a very, very clumsy scheme. It's very analogous to, why was multiplication invented? If you had, try doing, 4 times 1000 without multiplication. 4 plus 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 4 plus. It becomes extremely cumbersome. You need to invent essentially a shorthand way for carrying out that computation. You can manipulate vectors using these rules, no problem, except the only problem is that it becomes very cumbersome. You have to draw arrows all over the place. Just like why did you need to define this idea of the derivative function? In principle, given the graph, if given a function, you can plot a sketch of it, and then if I ask you what's the rate of change of this function, you just draw a tangent line at that point and then measure the gradient of this tangent line. The only problem, of course, is that is extremely cumbersome. You wouldn't want to be drawing tangent lines all over the place. In exactly the same way, you wouldn't want to be drawing arrows here, there, and everywhere, okay? नई मूवी का टाइटल आ गया है. Anyway, okay, so you want a more convenient way to write down these vectors mathematically. Okay, go back. You think of this position vector, this arrow. You realize very simple terms. अब जाके आपकी असल में एक्सिस आई हैं. अभी तक आपको एक्सिस की खास जरूरत नहीं पड़ी थी. Everything I wrote down over there was independent of any axis, independent of any coordinate system. कोई arrows है, यूं arrow add कर रहे हो. The fact that I took 2 steps here, 2 steps there, everybody will agree on that statement. That's independent of any coordinate system. कि मेरी starting location वो है, मेरी final location ये है. Okay? So for example, इधर कोई pressure pad है, उस पर मैं कदम रखता हूँ, कोई बम फट जाता है. Everybody in the universe will agree that I will die after a short time. There can be no possible disagreement about that. The description of how I died may be different. कोई कहेगा कि आपने 2 steps इस डायरेक्शन में लिए थे, फिर 2 steps उधर लिए. कोई कहेगा नहीं मैं उल्टा देख रहा था, इसने 2 steps साउथ लिए और फिर 2 steps इस तरह लिए. Okay, but I died. Okay, so That is true in any coordinate system, okay? So that's what I meant, okay? These manipulation rules are independent of which coordinate system you use, okay? But given now that I have set up my axis, using these axes I can very neatly mathematically describe these arrows. And that's essentially what we'll start doing next time, but the basic seed of the idea is this. It simply boils down to that given this white arrow, I can write this white arrow as a sum of two arrows because I know how to add arrows. One of these arrows lies along the x-axis, the other arrow is parallel to the y-axis. Essentially, one arrow is in the same direction as the x-axis, the other arrow is in the same direction as the y-axis that I've set up. If this arrow is of size ax, let's say that this is vector A for generality, and this is of size ay. So ax is the size of this horizontal arrow, ay is the size of this vertical arrow. Okay? How do I write down this original white arrow? Well, of course, आप कहोगे A is equal to ax plus ay. मसला नजर आया? This is a number. This is an arrow. ये गुनाह कबीरा है फिजिक्स में, okay? There are many sins I can forgive. Not this one. Unfortunately, मैं आपको पनिश के बजाय मेरा खुद दिल करता कि जाके खिड़की से छलांग मार दूं. Okay, but that essentially is an illustration of how cardinal this sin is. कि देखने वाले कोई कहता है अस्तगफिरुल्लाह और छलांग मार देता है. Okay. Okay, so don't do this. Don't make this mistake. Never ever should your equation be a vector equals a number. A vector can only be equal to another vector. A number can only be equal to another number. Okay? So that's essentially where so think about how will I be able to write this white arrow as a sum of these two arrows. That's where essentially we start off from next time.